Good morning, everybody, and welcome to the third session of the second cycle of the Quantum Technology Training for Policymakers. And today we are going to talk about the use cases of quantum sensors, and in particular about gravimetry and navigation and mine clearance. I would like to shortly introduce you the training session and our speakers. Here we go, the very familiar slide. And as I noticed already, so the use cases session is today. Please note that this is actually our, so to say, Christmas session, because this year is the last one for this year. And the next one will be waiting for you in January 30, and it will be about the efforts and investments beyond the EU and quantum technology, of course. So as always, I thank a lot the CNR-INO, that is organizing team of this training set, and also the Quantum Flagship Coordination Project, QCATS, which is setting up all the stage. Today, we hope again to gain knowledge, to get better informed decisions and cooperate with peers and also with the members from other countries. I remind you that we receive usually the participants from many countries, like 31 in particular, and from all European Union countries as well. And most of you are very well informed about the decisions, about the quantum technology state of the art, and they want to keep informed. So that's why we are having these monthly trainings. But there are also a lot of people that are wanting to get into the field and are following us to receive more information. We also know that among you, there are people from government, from companies, from research and academia, and this is really nice that we cover such a broad spectrum. This is the countries set that we are covering, and I remind you that today we are going to talk about the use cases on quantum sensors. Our first speaker of today will be Philippe Bouyer, and he's a researcher at the France National Research Council, CNRS, and he's a research director and also a professor at the University of Amsterdam, and as well an Eindhoven University of Technology. And he's a specialist in laser cooling of atoms. After completing his PhD at the Karsler-Brossel laboratory in Paris, he moved to Stanford University and then to the Institut d'Optique, where, among other things, he now carries out the first. He carried out the first experiment on matter wave quantum sensors and quantum simulators, which are among the topics of our session today. So he founded also a company called Photonic, and wait a second, I'm getting to the company, but before the company, he found the Numeric and Nanoscience Laboratory, and also Muquans, a startup, which is in Bordeaux. And he is now in charge of the science and technology of the National Quantum Delta NL initiative. Philippe, please welcome on stage, and we are looking forward for your presentation.
Thank you very much for the introduction. I think you need to stop sharing for me to be able to share, actually.
Exactly.
Yeah. Okay, now that should work. Yeah, thank you for the invitation to give a quick overview of quantum sensing and give some insight on some use cases that are already in our hands with this technology. What are we speaking about when we speak about quantum sensing? We are actually speaking about a lot of things, but they all rely on our capacity, our ability to control and manipulate very tiny objects, quantum objects, with extreme sensitivity and extreme accuracy. And these tiny objects, well, because they are quantum objects, they are very sensitive to their environment. And if so, by measuring how sensitive they are, we can get insight quantities of the real and the outside world. For instance, you can use lasers and atoms to measure time extremely precisely. That's what we call atomic clocks. And this is among the most precise clocks in the world that we do with these quantum sensors, and they are basically used to define worldwide timing today. We can also cool down atoms to temperature almost close to the absolute zero. And in this case, we can build sensors that, and I will give some examples that can actually measure gravity extremely precisely or measure rotation extremely precisely, and also can measure magnetic field and make magnetic imaging. We can also manipulate tiny defects in diamonds or tiny defects in silicon. And these tiny defects behave like single quantum objects, and they can also be extremely sensitive to temperature or to magnetic field or to pressure, etc. And you can also use light and really create some very weird quantum state of light that can enhance our way to get images with very tiny signals, for instance, for radars, but also for biological applications. So the idea of a quantum sensor, and I will not give you a class on quantum sensing, but if you want to learn more, you're welcome to come to Eindhoven and attend one of my classes. I'm just teaching this actually today. It's based on our capacity to actually take a quantum system, which you can see as a qubit or a spin, and then manipulate this qubit in all kinds of directions by using light fields, electric fields, magnetic fields. But we do it in a controlled way, which means that we know exactly what we are doing to this quantum system. And then if something happens, that will change basically the outcome of this control sequence that we have applied. And we know exactly then why it happened and what basically is the quantity that created it. If you think of a sensor, it is very important to know how basically your sensor, in this case, basically our quantum system, is actually changing and giving you an outcome of the quantity which is actually affecting it. For example, if you want to measure tension like a current in your home, you're using a voltmeter and you look at the needle and the needle tells you, oh, there are like 220 volts or something like this. In our case, the quantum sensor is doing the same thing. And you can then define the quality of your sensor by looking at how sensitive it is. So that means how well it can look at tiny changes. In that case, that means that the precision of your sensor has to be very good. Each time you're doing a measurement, you need to be very close to the previous measurement. If you look at the graph on the right, this is like a shooting with the yellow dots that are on the bottom right of the graph, where you can shoot all the time at the same place. And then if something changes, you can do it very well. But you can be completely off. And a lot of classical sensors need to be calibrated in order to be sure that these tiny measurements or these tiny dots on the graph here are actually centered as on the top left picture on the graph. In that case, you have accuracy as well. And very often when you do this calibration, you need to redo it many, many times because the accuracy is actually drifting and your system is not making the proper measurement anymore. The quantum advantage of the sensor is it can be sensitive, so you can really look at tiny changes. It is accurate, which means that each time you're doing a measurement, you know exactly that what you have as an outcome of the measurement is what you expect. And it is long-term stable because all the properties of this quantum sensor is driven by the laws of quantum mechanics. And this is why we have started to foresee a lot of advantages of this sensor. And there is another advantage of the sensor is the fact that in many cases, the quantum system is affected by a quantity, even if it's not touching it. For instance, you can measure gravity, but you don't need to actually wait for the quantum system to fall on the ground like Newton did with the apple to measure gravity at this time. You can measure magnetic field, but you don't need to send something to measure it. Just the sensor itself can measure it. So in a certain way, we are so sensitive with this quantum sensor that we can see without being seen, or we can see without disturbing actually the environment that we are trying to look at. And this has many advantages. And of course, this sensitivity comes from the fact that the single quantum object actually has a very strong shift in its properties due to this external perturbation. And also that these qubits that we can use to do the measurement can even enhance the measurement thanks to the weird quantum properties that we call entanglement. So the fact that we have very tiny systems, the fact that we can use very few of these systems, but still, thanks to the quantum properties, we can have a very high sensitivity, which means that we can measure it with a big precision, we can have big signal out of it, makes this sensor extremely useful for many applications where it is very hard actually to do accurate measurement without going into the system or without being having a strong interaction with the system. One example of application of this sensor is our capacity to survey or to monitor, for instance, gravity. And this allows us to look deep underground, for instance, without the need to dig in. There was an example that was showcased last week in Lisbon, where such a quantum sensor, aka a quantum gradiometer, which is using cold atoms to measure actual gravity. And with 2 clouds of cold atoms, we can measure the difference of gravity, how gravity changes with the height. And thanks to this, you can look at an underground structure like a tunnel, or in this case, a sewer. But so this is doing a map, but you can also like put this sensor and leave it there for a very long time because, as I mentioned before, they are very stable. And in that case, you can look at tiny changes in time. And that can allow you, for instance, to look at whether the water of the rain is indeed going deep underground and filling back the water reservoir or the aquifers. Or you can put a gravimeter on the top of a mountain. The picture showed here is a gravimeter which is sitting on a volcano. And then you can actually look at the change of the magma mass inside the volcano. And of course, there is no other way to actually look at the magma mass unless you are looking at a volcanic eruption. Another way to apply it is because you have this sensitivity, but also this accuracy, you can make extremely precise maps. And you need this kind of maps. You need extremely precise maps of gravity in order to understand how the Earth is actually changing over time. And you can also need very precise maps of magnetic field for the same reason. The magnetic field of the Earth is actually also a signature of the health of the Earth and how it evolves. But as I will explain in the next slide, it can also be used really as map to find your way and to find your position. And for that, you can also use the capacity of the quantum sensors to be extremely accurate, extremely precise, and also stable over time. And this is an example of a magnetic map on the bottom right, and some gravity map also that were obtained with actual, for the gravity map, it's been obtained actually with a quantum sensor on the boat that you see on the picture. One application which is also extremely interesting, extremely important, especially today, is our capacity to get better positioning, better navigation capacity, and also better timing. I already mentioned the clocks, and even today we need quantum sensing to measure time, this what we call atomic clocks. These atomic clocks are also actually the base of our best position navigation and navigation system, the GPS. It has to use timing in order to measure the time a signal goes from the Earth to the satellite, and by using many satellites, you get a very accurate position. But what if the satellites are not available anymore? Or what if the signal to the satellite is jammed? Then you only rely on your capacity to measure your position with the maps I presented before, or by recording your acceleration, your attitude, and then making some very complex operation for it, which actually is very sensitive to the quality of your sensor as well. And again, quantum sensors can really make a difference because they are accurate and they are stable in time. They have no bias, and this bias is actually the leading factor of inaccuracy in your navigation. And I give a few examples of some studies that have been done in the US and also in Europe on navigation protocols that actually use quantum sensors to mitigate GPS failure. Last but not least is the prospect of using these sensors for all kinds of biomedical application as well. And For that, for example, you can use your capacity to measure magnetic field extremely precisely. And if you put a lot of these tiny magnetic sensors around your head, you can actually do some magnetic imaging of your brain activity, which can be very important to treat some disease, but also maybe to make some connection between the numerical world or the virtual world and the human body. As well, you can use quantum sensing to enhance your imaging capacity, to make imaging much better, to detect actually in cells, to detect in your body some different things like blood pressure, like the heart rate, and etc., without the need to have a probe inside your body as well. So this is an ongoing development, but there are lots of promises, and you see again a few examples of a few prototypes of such applications of quantum sensors. So there is a lot yet, lots of use cases that are identified. Lots of these use cases are actually being studied extensively. There are lots of programs. There are also infrastructure that are building up to actually get these studies and really prove and go to the next step with these sensors. But there are still a lot of challenges. We are just at the beginning of studying this use case, and the more we do, the better we'll know what the impact can be of these quantum sensors. And of course, a lot of the picture that I showed are still like very big sensors, very bulky sensors. Even if we have commercial sensors, they are still big, that they cannot actually be deployed on a large scale. And the challenge there, again, is to make more integration and to go to photonics integration, to go to chips integration of the sensor in order to get it widely diffused in a large, in many areas of applications that I mentioned before. And I think I will stop here. Thank you very much. And if you, I think there is maybe some time for questions now. So I'm happy to answer it.
Thank you very much, Philippe. This was exciting presentation. I learned a lot of new things, and we actually have a dedicated question and answer time for about half an hour after the talk. And I would like to invite now the second speaker in the meantime on the stage, and also invite all the participants to write questions and comments in the question and answer section here in Zoom. So then we will read them out loud or invite you to speak. And our next speaker, which I would like to invite on stage right away, is Guglielmo Maria Tino. Please, Guglielmo, come on stage. And Guglielmo Maria Tino is a full professor of physics of matter at the University of Florence. And there he leads a research group at the Department of Physics. And he's as well associated with the LENS laboratory, Italian National Research Center, CNR, in particular National Institute of Optics, and also with the National Institute of Nuclear Energy, INFN. So he graduated in physics from the University of Naples, Federico II, and received his PhD from the Scuola Normale Superiore in Pisa. Then he was a researcher and associated professor at the University of Naples before moving to Florence in 2001. So he spent extended research period abroad as well, in Gila and then NIST and Boulder, Colorado, and at the École Normale Supérieure in Paris. So Tino had secured funding as a national as well as an international PI for many projects. And in the 2015, he also founded a company. So AtomSensors, s.r.l, it's called, and we hope to hear about it today from him. And this is a spin-off of University of Florence. So I welcome Guglielmo to present about his work, and we are looking forward for the presentation.
Yeah, thanks for the introduction, and good morning to everybody. So I should share my
Your
screen. Here it is. Is it working?
Yes, it's all perfect. Thank you.
Okay, so let's go. So I gone on this introduction to quantum technologies and applications, and in particular, I will tell you something more about quantum technologies based on ultra-cold atoms. I will not go in details, of course, but just to give you an idea, ultra-cold atoms are produced using laser light. So you know that at room temperature, we are about 25 degrees centigrade, but in physics, there is an absolute scale of temperatures. There is an absolute zero, which is about 273 degrees below zero centigrade. And so using the pressure exerted by light on the atoms, we can experimentally, it's not theoretical, we can produce gases of atoms that have a temperature very close to the absolute zero, a few microkelvin or nanokelvin. So essentially the atoms go to the absolute zero. So very low temperature means very small velocity. So these atoms are moving very, very slowly. And also using laser light, they can be, as we say, trapped. So essentially you can start from a gas in a cell, which is at room temperature, and you can produce a gas of atoms containing about 1 billion, 10 billion of atoms at a temperature which is, as I said, close to the absolute zeros, and trapped in a volume of the order of 1 millimeter cube. Here you see, for example, in our experiment at the Lens laboratory in Florence, a cloud of strontium atoms in particular. The light that you see here is the light emitted by these atoms, about 1 billion of atoms of strontium, that are trapped in this vacuum system using this blue light produced by a laser source. And these atoms, as I said, have a temperature which is very close to the absolute zero. When you go smaller and smaller, lower and lower in temperature, you can achieve the condition that was predicted by Einstein and Bose, that is the Bose-Einstein condensation. This is a quantum effect that can only be observed with these very cold atomic gases. Now, in quantum mechanics, you probably heard that not only photons, but also particles like atoms and molecules have a double nature. You can consider atoms, as we usually do now, as extremely small particles with a mass, but also a sort of a wave. And this wave has a typical wavelength, which is called the de Broglie wavelength, that is inversely proportional to the velocity of the atoms. So, as I said, using laser light, you can reduce the velocity of the atoms, and this means that the wavelength of the atoms becomes larger and larger. So essentially, the atoms become a sort of wave. And so, for a wave, it's not strange what is shown as a paradox in the cover of this book. You know, for ourselves, for a skier, as it is shown here, it would not be possible to go on the two sides of a tree. It would just smash on the tree. While for a wave, this is normal. A wave, if there is an obstacle, it can go through two different paths and then eventually recombine. And so this is possible also for atoms. As I said, if you consider them as a wave, the difference for atoms is that the important feature is that the atoms have a mass, and so they are affected by gravity as all systems that have a mass. And so we developed systems that are called atom interferometers, that are, as was said already, very sensitive and very accurate sensors of gravitational effects. For example, this is the first gravimeter that was demonstrated now a few years ago in Stanford. by the group of Stephen Chu, who got a Nobel Prize in Physics. So here you have cesium atoms, but this is, I mean, you can do it with many atoms, but essentially these atoms are cooled down, as I said, and then launched vertically in what is called an atomic fountain. And while the atoms fly and then fall down, with some laser pulses, you can, as I said, split the atoms and recombine, as was the case for the skier before. But there is gravity acceleration in the meanwhile affecting the atoms. And so the signal that you get, the output when you observe the atoms, is affected by gravity. And for example, here you see the signal produced by the moon and the sun, what is called the tidal effect, the effect that produces tides also on the water of the sea. And so this, as you see, can be observed with very high sensitivity and also very high precision in general, as it was explained before. This is an example of an atomic gravimeter, but also you can combine in the same atomic fountain two gravimeters, and then you measure the gradient, the difference of gravity in two different positions. And this is in fact an example of the gravity gradiometer that we developed in our lab in Florence. And to test this system, we had some masses, here these cylinders, that we were moving in different positions. And this is the output of our sensor. You see that depending on the position of the masses in the red position or the blue position, we get a very clear difference change in the output signal. So essentially, we can measure gravity, the gradient, what is called the difference of gravity in two different positions. And this we use to measure, to have the first measurement of the Newtonian gravitational constant with an atomic sensor. But also with the same system, you can launch 3 sets of clouds, 3 small clouds of atoms. And then you measure the additional derivative, what is called the curvature of the gravity field. And so this is the demonstration that you can measure gravity with different, with the same kind of apparatus. The system is the same, but modifying the procedure, you can measure different features of the gravitational field. And this has important applications because depending on if you measure gravity, gravity gradient, or gravity curvature, you can detect different kind of sources that affects the gravitational field. So these kind of sensors have had a rapid development in the last decade, I would say. And so now they are already the best gravimeters, as we anticipated already some years ago, for example, in this paper where we were comparing the classical gravimeter based, for example, on a spring or a falling tube with the quantum sensors that already at the time were we were anticipating to be the best sensors, and now it's this is a reality, I would say. Atom interferometers is an important example of a quantum sensors. The other one that was already mentioned is atomic clocks, and in particular the optical clocks, where the tick-tack of the pendulum is produced by the light, the electric field of a laser light. And now the relative precision of these clocks in our labs is already reaching the 10 to the minus 20 precision. 10 to minus 20 means that you have a relative precision of better than 1 billionth of a billionth. So this means that these clocks can be wrong by less than 1 second over the duration of the universe. This is amazing, but also something which is striking is that if you consider an effect of general relativity, which is called the gravitational time dilation, This is the fact that gravity affects the ticking of a clock by a very small amount, which is, if you make the calculation based on general relativity, is 10 to minus 16 per meter. So if you move a clock by 1 meter, lower or higher on the Earth, its ticking will change by 1 part in 10 to the 16. That can sound like a very small effect, but in fact already on the GPS clocks that are orbiting around the Earth, and that's what said, are giving us our position and allows us to move around, you must take into account this general relativistic effect. Otherwise, this clock would be wrong by a considerable factor. But now with these new optical clocks, what was so far important for a distance of 10,000 kilometers, it was shown very recently, a couple of years ago, in papers published by some groups 2 years ago. Now you have a resolution of a few millimeters. So you can see this effect of general relativity if you move the clock by a few millimeters. So putting all together, you see that these atomic quantum sensors, either atom interferometers or optical clocks, are now very sensitive quantum sensors for gravity. And so you can have different applications for mapping of natural resources, geodesy, navigation, the investigation of ice sheet changes and sea level changes. Of course, you can have experiments in space, but also it was shown the possibility of using these sensors on the ground with several important applications that can go from fundamental physics to meteorology, geophysics, space, civil engineering, oil and material prospecting, and navigation. And for that, as was said, there were already now different companies that started producing these quantum sensors as a commercial system. I think the first one was started in Stanford already now a few years ago. And as was said, now there are a few in different countries. And for example, we started this AtomSensors company as a spin-off for the University of Florence. And with that, I think I've finished my time, and thank you for your attention.
Thank you very much, Guglielmo, for these insights into how well and why atoms actually help us to sense, as well as light. This was very interesting and deep. And I'd like to invite back Philippe to the stage and open our question and answer session. We have really nicely about 20 minutes to talk about various curiosities and questions. And we already have a couple of questions sent to us. Please provide more questions via question and answer sessions, or raise your hand in case you'd like to ask a question loud. So let's start from the first question, and I'd like to address it to Philippe for the moment. The question is about medical imaging. So is there any use, a use case in particular for commercial use of such sensors in medical imaging, to your knowledge?
So from what I know of, this is some of them I showed already. So there are some, let's say, proof of concept, probably mostly on this brain magnetic imaging systems that are using, in most cases, I think, magnetometers based on vapor, like atomic vapors. And I know that in the US, the company Sandbox AQ has also started to develop a magnetocardiogram, so to measure the the cardiac activity in the whole body, but through the magnetic activity and not the electric activity as usual. They have like a test machine there. Of course, commercial use for this kind of medical application is always tricky because it's a long process. I know also that there has been some development with NV centers to increase imaging, but also like optical pumping of some gas for better imaging. So there are a few proof of concept. There are a few companies that are starting to actually startup companies that are starting on medical application of NV centers, for instance. There is one in the Netherlands that just started like a few months ago. So it's building up for that.
Okay, thank you very much, Philippe, for this for sharing with us. Guglielmo, do you have also some insights in the commercial use cases of the medical imaging?
Yeah, that's not my field. It's just what I heard since some time. This is not a new idea. What is important is that now the technology advanced so much that this is again becoming a reality. And as far as I know, as Philippe said, one of the issues, I mean, the technology is there. The sensitivity of atomic magnetometers was already proved, and it's competitive. Then it depends on what you are interested in, but it's competitive with other magnetometers. The demonstration of the applications in medical in the medical field then must go through procedures that usually take longer than in other fields.
Right. Yeah, I'm very excited about it. I'm looking forward when our hospitals will be empowered by new, cheaper devices, because this is also a promise of at least an atomic vapor cells. And let's see how it goes. So let's go to the next question. And this is regarding to the challenges experienced in the field. So Abdullah Asmari is asking, what is limiting in the development of quantum sensors? Is this a supply chain, or is this the limitation of existing photonic optical components? Or what light sources wavelengths is predominantly used in the quantum sensors that are shown in your presentations? Let's start maybe with Guglielmo, and then Philippe could join.
Yeah, of course, technology, I mean, seems, as we showed, the basic idea of these sensors, the ideas go back now to a few decades. Then the practical applications depend on the available technology. But these things, in my experience, one pushes the other. So, for example, I showed that trap of strontium atoms. Strontium atoms was investigated later than other atoms because the lasers that you need are more difficult to produce for technical reasons. But then when it was found, also thanks to our experiments, that these atoms had some features that are particularly useful first for clocks and now also for interferometers, then, there was an interest, and then the necessary technology was developed. So this is the example of something that was difficult until some years ago, and now many labs are working and developing systems based on strontium. The technology is much more advanced for other atoms like rubidium and cesium, because these were already used for applications like GPS, for example, since a long time. So at the moment, I would say I don't see a showstopper. Depending on the goal, the technology, there is still space for making things more robust, more compact. And we have projects also in the frame of European collaboration for developing this system for space where you need things which are compact, reliable, sensitive, and so on.
Okay, thank you very much, Guglielmo. And what is your hold on this, Philippe?
Yeah, well, maybe just to complement what Guglielmo said, he already said a lot. Well, one challenge is indeed to get a proper supply chain for many sensors, in the sense that a lot have been done in the labs, but it's still relying on, let's say, technology which is accessible at a high price. I mean, you have lasers, and the question was about lasers. They're mostly visible lasers. So for NV centers, it's going to be around maybe like 600 or 700 nanometers to the infrared, 800 nanometers, sometimes also in the near infrared, 15 nanometers, like the 1500 nanometers, like the telecom band. So all this light is available. Very often it's still an expensive technology because it's only a small market. So it's a little bit the chicken and the egg. In order to get more applications, you need to get this cheaper, but in order to get this cheaper, you need to get more applications. So and I think that's where we really need to have these programs where we not only look at developing the technology, but also developing the use cases, making these use cases available, really get this bridge between what is in the lab at a quite high price, where you can still have a certain level of integration, and what can be scalable in terms of price and integration. And this is good for any sensor, not only atoms. Atoms are maybe the most complicated ones because the laser system is very complicated. But if you think about NV centers, you need also to have a supply chain of diamonds, for instance. And this is something you need to get at a certain level of expertise and etc. in a professional way, not just in the lab.
Okay, so this is the supply chain challenge at the moment. Indeed, is important. So I hope that these programs that have now been launched, that these pilot lines, will somehow help sorting this out and somehow welcome indeed to participate in use cases building and somehow provide the growth of the supply chain. Let's hope this will work as hoped. And I'd like to invite Michael Botzinger to ask his questions because it is the hand up. I welcome Michael. Could you talk, please?
Sorry, I didn't have a question.
Okay, so it was by mistake. No worry. So we are experimenting this option. This will work. Thank you. Then let's go further for the questions in the chat. So there was a question about gradiometers. So from Angela Paredes Galan and from Angel, I'm sorry. So the question is, so you talk about measuring gravity with two atomic fountains. So I suppose that was to Guglielmo. And but as you said, you could also see the difference in gravity by comparing frequency of atomic clocks at different heights. So could you compare both possibilities and what is better?
Yeah, I think it's an interesting question. In practice, a gravity gradiometer is the one that I showed that we use developed in our lab. Is something in principle relatively simpler as an apparatus to measure the difference of gravity accelerations in two different positions, nearby positions. For a clock, it's something that until 3 or 4 years ago would have seemed almost crazy to consider. But there was such a quick advancement that this became. There is a difference. In one case, we are measuring essentially the change in the acceleration with the gravity gradiometer, the atom interferometer. The two clocks measure a difference in the gravitational potential. But this is an interesting question, I think. It's something that just became possible recently. And I would say that the combination of these two, for example, an important application is the possibility of comparing gravity on the two different sides of an ocean. Because, you know, sometimes there are classical instruments to, in Italian is teodolite, I don't know what is the English. It's a system where you go point by point and you look at the difference in the position. But if you are on one side or the other of the ocean, you cannot compare the, while you can use two different clocks to measure the difference in the potential. Essentially, you get the geoid, you get the profile of the gravitational potential, and For example, using a reference in space, you can compare the gravitational potential on the two sides of the ocean.
So this is practically an invitation to the Angel to collaborate with Guglielmo, because I think there is some study to do here. This is very nice. And there is next question to Philippe.
Maybe I can briefly add something.
Sure.
As Guglielmo said, I mean, that's a different way of measuring gravity, and it's not measuring the same thing. And actually, each of this class of instruments has a different scale of measurement. Like if you take clocks, as you say, it's very good for measuring like the geoid between continents. And it's actually you also look at effects that are coming from very deep into the earth, into the ground. So the scale, so it's for very large scale measurement, like a space mission, for instance, is even for bigger scale. If you take gravity now, it gets a certain scale which is reduced. If you take a gradiometer, it will actually look at details. It's much smaller scale, but also it will be not so sensitive to very deep changes. So this is really each instrument has a different scale. The combination of it can actually, for making a gravity field map, you need lots of different scales and lots of different corrections. So you probably need this combination of instruments at the end.
So then we face the compatibility, actually. So they complement each other.
They complement each other, and some can be stationary, some can be in space, some need to be transportable to do the maps. So this is the variety of the application of quantum technology for different aspects that, I mean, the big instruments we have, they are very useful. They can be reference points, they can be reference points over time, over a very long time, and then you can have tiny systems that deploy. The example I showed on the volcano, which is actually in Italy, it's on the Etna. It's a combination of a reference point with a gravimeter and tiny measurements done with MEMS, for instance. So the network of accelerometer with the MEMS is giving you some like short scales information, but of course they are not perfect, and then they actually refer to the reference of the quantum gravimeter.
Very nice.
If I can complement on the complement, but also to answer more to the previous question about technology, as Philippe said, eventually you would like to have a network of these sensors. If you take, for example, Etna, but I know more about Campi Flegrei, around near Napoli. There is an area which is going up and down by meters because of a volcano. It's not Vesuvius, another volcano which is pushing a town up and down. And it's a super caldera. It's a very dangerous area. And there is a network of tens of sensors to monitor the evolution of this. So it would be nice to have tens of atomic sensors there. The problem is that each of these sensors, I mean, orders of magnitude, the cost is a few hundred €. So as Philippe was saying there, was saying before, having a network of quantum sensors there would strongly improve the monitoring. But you know, in practice, having 10, 20 sensors, each of them costing, I don't know, 100 to 1 million, 100K to 1 million euro at the moment is hard to realize. But if the technology advances, then eventually the price would be comparable to the cost. The cost would be comparable to the classical ones, with orders of magnitude improvement in sensitivity, accuracy, long-term stability, and so on.
That's a great prospect. That's a great prospect. I think we have now one more question that will help you to highlight again the need of s.r.l sensing. So there is a question to Philippe about the magnetic map for navigation purpose. So what is the status of the magnetic map today for the navigation purpose? And I think you mentioned Sandbox AQ as the provider of such
Yeah,
maps.
so it's I'm not sure I have the full information about it. So that depends what you say about map or about the concept of using map for navigation. I think the map, there are maps about anomalies. They probably need to be, or they will probably need to be improved if it's really useful for navigation. Now, what I know is there's been a first test a few years ago of that was performed by the US Air Force, where they put basically a magnetometer, and at this stage that was not an NV center, so there was and there is a difference. The NV center is measuring the magnetic field, so really like where it is pointing, the direction, and etc. Where most of the magnetometers that have been developed with vapors, they are making the magnetic amplitude, basically. So, but still you can do things. So they had that. And there are lots of problems that they had to put it like on a stick hanging out of the plane, because otherwise you have magnetic perturbation. But they did a proof of concept of this map navigation. In the Netherlands, we also started a program, also defense related, on developing this and also making simulation about this. And as I mentioned, there was a recent press release by Sanders AQ that they have done something similar. So that's what I know of in that case about the progress. So I think there's been proof of principle and also like simulation where they built, let's say, a digital twin of the quantum sensor and put it in their navigation processing units in order to actually simulate how well it could recalibrate a normal inertial navigation system without the GPS. And they showed, so the proof of concept is done. So basically now you need to put it on the field and measure it.
Mm-hmm. Thank you very much, Philippe. Now we have also a question from Philippe Grandier. He's asking whether there were ideas to propose for connecting several or very many actually gravitational sensors for global Earth survey. So do you know about the projects in this?
Yeah, so I can answer this one, and in parallel, maybe the question of so sorry the name, but Hovje Kalik. Sorry if I did not present very well about Carioca PMP that Guglielmo already mentioned. So it's work under progress in terms of a network of sensors that are connecting together. There are still, when there is a first initiative, which is actually pushed by the under the Flagship program by the Commission, European Commission. This is this call for a network of quantum gravimeters. It's a proposal, so there's been even though in that framework it's really to get maybe very quickly some actual results. So the vision of the large network, which would require a very long process of deploying, is not there yet, but it's the first step towards this vision of a large network. It's also important because you need to know what you need to do. And it also connects to other networking initiatives because you have in parallel a time and frequency network. And if you want to connect this gravimeter lately, you will need to connect them to the time and frequency network or to the clocks. And also this European like quantum internet networks that then would actually connect with quantum states instead of, let's say, phase stabilized states like for the quantum metrology network. So all these different aspects of the different infrastructure, at some point, they will hopefully rejoin and be the first like the fertile landscape for building this connected network of gravimeters that will give the necessary time survey for it. One thing which is important, because we also discussing with like the political deciders, is these things take time. If you want to prove that a gravimeter can give a result, I mean, you need to study, you need to build a gravimeter, but this we can do now, but then you need to actually wait 1 year, 2 years, maybe 3 years, because the things we are looking at are very slow. So you cannot just say, I'm going to do something, and in 6 months, I'm going to get the result and know what is the next step, because in 6 months, you might miss the right event that you are actually looking for. So it is very difficult because it takes a lot of time to actually make these proofs. And that's where we really need to engage much more with end user cases in order to have the time to make the proof, but at the same time foresee the future, because otherwise it will take way too long to get to these networks.
This is really nice reply. Thank you very much, Philippe. And actually, there we have a direct question from Oscar Diaz here, who is asking, at the European level, what should be done according to you in order to move faster these technologies closer to the market and industrialization?
I don't know. Do you want to fire first, Guglielmo? I already spoke a lot.
No, it's an interesting question. I think, I don't know, I don't want to take it too long. I think it's a typical European issue. I mean, essentially, these technologies that we presented, as was said, these are difficult technology. I mean, it takes time, takes efforts, but I mean, in the labs, we know how to do things. There are companies, as we said. The question is political decisions. We are talking to policymakers. There should be decisions. And these decisions in other countries have already been taken. I mean, these technologies in the United States are already, we don't even know what is the level, because it's, it's needless to say that we are talking about technologies that are very often dual-use technologies. And so for some applications, these are going very fast. And US and China are examples of countries that, and I guess also Russia, that took seriously the importance of these technologies. In Europe, I would say we are a little bit slower, and but slower in terms of political decisions. We are fast as scientists. In Europe, we have all the know-how, and many of these things have been developed in Europe and maybe applied elsewhere.
Do you see some change that can be done so to speed up a little bit?
Yeah, well, there's probably a way, and it's not only for sensing. I think it's for all quantum technology. Is if we want to go to the market, you can say it two ways. You can say it in a push way. Let's say I need the technology to exit the lab and to become a company, or you can also try to pull it to say I need end users to really, or I need potential users to really endorse this technology. And the problem is if you're not ready now, it's if you wait to be ready to get the end user, you probably don't know what to do. But if you wait for the end user to decide to use the technology, it will probably never happen, because they have to be convinced. This is something we experienced, for example, where we discussed with oil and gas or other aspects of it. So I think you need to help the end users to actually try to use a technology which is not ready, but just to get used to it. And this is the missing ingredient that we have. It's like how do we actually favor? And I think that's where the US, like Sandbox is one example. They're able to go to a company, and the company, I don't know how, because they have like billions of dollars, like Amazon. They actually try to use the technology just because they want to try it, and they don't really know what it is going to be good for. But you learn a lot from it. And I think we need to get something in Europe that favors this process, where end users really use the technology in order to adopt it, but not wait to adopt it before they use it. I don't know how to do it, but I leave the question back to Oscar, who asked this question.
It is a good start of the discussion. So it hits somehow the big player, which can allow himself or herself to play with such a case and invest enough money. And now we just need to decide whether this big player is a public entity or the private entity, and see how it goes on the way. Thank you very much. This was a great session. We still have some questions left, and this is a good sign, which means there is a lot of interest, and we will actually continue discussing sensing in one of the following sessions. And I hope then we will address more of the coming questions. Thank you very much, Philippe, and thank you very much, Guglielmo, for being with us. And
thanks for your attention.
It was a really great pleasure to...
Thank you very much. It was a pleasure. Thank you to the attendees for all this great question. That's what makes the session successful. So thanks a lot.